All right, and so now let's look at example 2 for finding arc lengths right here. So now I'm going to spend some time writing down the wording description of the problem. So on the board here, in our example 2, we would like to find the arc length. Okay. So the graph here is the curve from the function f of x equals 1 over 10 times e to the 5x plus e to the minus 5x. Okay. And then this is an arc that's on the interval from minus natural log of 3 to positive natural log of 3. Okay, and so now let's have a full view and let's have a close look at the wording of the problem here. So this problem, in the way how it's instructed, in the way how we are instructed to do with the problem with this piece of arc right here. So we have the graph here is the graph that came out from the function f of x equals 1/10 times e to the 5x plus e to the minus 5x. Okay, and we restrict that function, that graph inside the interval from minus natural log of 3 to natural log of 3. Okay, but so unlike example 1, where I started out with first steps indicating that set up the integral to evaluate. So now if we're looking back at example 1, as a structure, it's a similar kind of problem. We have eventually, as a purpose, we finding the length of the piece of curve, the length of the arc that happened on this graph right here inside of that interval. But in example 1, I hope I explained that clear, but now I can kind of rephrase that a little bit. But the point of the wording of example 1, the style of wording in example 1 indicated that there is a chance, there's a likeliness that you only had to set up the integral and then no further need to evaluate that integral. That's the way how the example 1 was. That's why I started out with one separate problem. In example 1, I gave the curve, the description of the curve, and then I started out with the part A and saying that just set up the integral. And then in part B, if anyone learning from the video here was ready to use the technique to evaluate that integral, then we had a part B. And then at the end of example 1, I also explained that there is a chance, there's a likeliness that some instructors do not require their students to evaluate the setup integral right there. And so that's why the style of wording in example 1 indicate that yes, admittedly the purpose of the problem was to find the length of the curve, the arc length, but there's a likeliness that there's no need to evaluate that complete setup of the integral, because sometimes it could be a very challenging integral. But now if we're looking closely at this particular problem right here, example 2, it's the same purpose. We want to find the length of the arc, the length of the piece of graph that's restricted inside of this interval out of that function. Okay, but the wording here is get straight to the point, find the arc length. There's a complete different intention here. Yes, as the ultimate purpose, we're still finding the length of the arc. But in this problem, since it says find the arc length, that intentionally means we can actually find set up the complete integral. So setting up the complete integral is a must, because that's what we apply our understanding for this kind of material, this kind of application. Okay, but this problem here clearly say and clearly stated that find the arc length. That means after we set up the integral, then there's ways, and there's way, or the way to evaluate that integral, that complete integral setup is simple enough, or there's way to evaluate that integral. Okay, and so that's why with this problem, anyone viewing this video should have an expectation in mind that we will be able to go all the way to the end and obtain a final numerical answer for this length of the arc right there. Okay, and so just as usual, let's get started by setting up the integral. All right, so like example 1, I worked through example 1. There are always two choices, and I explained this when we were looking at the general discussion, when we were going over that general discussion, that once we have the curve, because here it's just a representation of the curve, but we have two choices. One choice is to set up the integral to integrate in respect to x, and one choice is to set up the integral to integrate in respect to y. Okay, what I mean is we have one choice of writing the integral as an integral from a to b 1 plus f prime of x squared, okay, with a dx. This is if we intend this, we're going to use this formula if we plan to set up the integral and integrate the problem and integrate that integral in respect to x. Or we also have a chance, we also have a choice to set up the integral as an integration that's in respect to y. Okay, and then I have also mentioned this in the general discussion part of our lecture here. Okay, so have a quick thought about this. I would see that in this problem, since the function itself was already in terms of x, then this choice would be a little bit more direct. Okay, I'm not making judge about how much more direct, how much faster or how much easier it's going to be, but at least this is going to be a little more direct right here because we already have the function f of x expressed and given right here. So things are already made a little bit ready for us. So all we do is just find the f prime right from there, okay, and then set up the formula, and then and even further the two integral bounds right here are already available. Whereas if we chose, it's not wrong, it's still going to give the correct answer. But if we chose going this way, then we're going to have to spend some energy. We're going to have to spend some effort rewriting this expression as an expression in terms of y. Solve for this, so we're setting y equals this right hand side and solve for x in terms of y. And then the interval here, the interval with the two limits left and right here also need to be converted to be re-expressed in terms of y. And so it takes more effort even before we can set up the integral. So it makes natural sense now that we stay with this. Okay? And so those are the two things that one wording of the problem, but a little bit, just a little bit of wording of the problem, but there are two intentions that we have to understand behind the scene right there. Okay? All right, so now I have my reason to clear out this other choice right here. I'm going to stick with this formula. Okay, so that means according to the formula that we're about to set up for here, then f prime, we just need to simply find the derivative here. And the function itself, right at first sight, it might seem a little complicated, but actually it's not that bad. We can go ahead and distribute this 1/10 as a coefficient into each term here. And each term here is a simple exponential function that you have seen it all over your calculus 1 material. Okay, and taking the derivative at this point, anyone learning in this video lesson right here should be fluent with taking your derivative. And so I'm going to rewrite f of x, just a rewritten form right here, as 1/10 times e to the 5x plus 1/10 times e to the minus 5x. That's my rewritten form of the function f of x. So that means my f prime. So f prime of x has to be, so the coefficient stays the same, 1/10 times e to the 5x, because it's the way how exponential function, that's the way how we take the derivative of exponential function. But don't forget, we have a little bit of chain rule that kicks in like that. So this is the inside function. So multiplied, the chain rule says we multiply with the derivative of the inside, so derivative of 5x gives me 5. Okay? And then that's done with the first term, that's done, that takes care of the derivative of the first term. So now we're looking at 1/10 as the coefficient of the next term, e times e to the minus 5x. That's how we're taking the derivative of exponential function. And then I'm going to multiply with the derivative of that minus 5x right here according to the chain rule, which gives me -5. And so now that is our f prime of x right here, the derivative of our function. And so in a more simplified form right here, then how about let me write that in the other board space. And so now our f prime of x can be rewritten in a shorter form to be 1/2 e to the 5x. So why 1/2 here? Because that 5 will cancel with that 10 right there, with that 110. And so same way here in the next step on my other board, I'm going to cancel the 5 with that 10, and then there's a minus sign compensates together with that plus sign right there. Okay, so in that way, now I'm looking at minus 1/2 times e to the minus 5x. So that's our simplified form of f prime right there. Okay, and so the way how I see is, and one more time, let's look back at the formula for our arc length integral over here. So to inside the square root, we need to square our derivative. So it's f prime all square. Okay, and then plus 1, and we put all that inside the derivative. So maybe before we setting up, so in my personal experience, I see it's better and more organized that we can just go ahead and find the square form, the square expression of the f prime right there. And then once we've had that there, then we're going to put it all together inside of the square root. Okay, and so that means now on this board of mine right here, I'm going to look at the square of f prime. Okay, so there's always a reason for doing anything. So squaring of f prime is going to give me 1/2 e to the 5x minus 1/2 e to the minus 5x, but all square. Okay, so that's what we do right there. And then, so now the integral is ready. That means the length we're looking for, the length we're calculating, is going to be an integral from minus natural log of 3 to positive natural log of 3. And then this is square root expression, and we're looking at 1 plus, and then the square of the derivative is here. So we're looking at 1/2 times e to the 5x minus 1/2 times e to the minus 5x. Okay, all square with dx. And that's the expression that's the complete setup of our integral right here. Okay, and so now, as I was explained earlier, the wording of this problem intentionally tells us that, even though it's not explicitly stating it, but it tells us that kind of behind the scene, it tells us that there's a way to evaluate this complete integral setup right here to come up with a final answer, final numerical answer. So let's find out how we can complete evaluating this integral right here. Okay, and so now, with an integral like this, now allow me to maximize this board space. So I am going to erase this work right here. Okay, and I'm going to rewrite my complete integral setup in the top line right there. So the length can be calculated by completing this or evaluating this integral. So square root of 1 plus 1/2 e to the 5x minus 1/2 times e to the minus 5x all square. Okay, and dx. So now we need the algebra. We really need the algebra. So the next step of this work right here, the integral is from minus natural log of 3 to natural log of 3. Okay, but inside the square root, I am doing the following. 1 plus, I am going to go ahead and FOIL out that, square right here, which is in your usual algebra understanding you should be able to carry through. Okay, so allow me to pick up the pace here a little bit. So foiling out that square here, and the 1 is not included with that. 1 is already a separate term outside of that square, so I'm talking about foiling out this binomial here. Okay, and so allow me to pick up pace on that particular one. So first term here gives me a 1/4 times e to the 10x. Okay, and you can algebraically double check with me on that. And then minus, and then here we're looking at just 1/2. Okay, and then here we're looking at plus, and then this is a 1/4 times e to the negative 10x. All right, and with a dx. All right, and so at this point there's still not much to be seen. The way to get to the final answer of this integral is still far away. Okay, because right at first sight right here, good luck finding an answer with that. And now we use the algebra to turn that into a slightly different expression. there's still no luck seeing where the final destination is on this integral. But now at least algebraically I can see that we can cancel out that these two terms here, this like term 1 and then minus 1/2 for here, they are like terms. We can cancel them out a little bit. Okay, and then by the way, I've got this because that was in my algebra, and you can use your algebra to double check, but you can also keep in the back of your mind that that term is constantly 1/2 e to the 5x but all squared. Okay, that's a little bit of explanation I have for you. And then so the same way with this, including the coefficient 1/4, this term itself right here is really truly came from a 1/2 times e to the minus 5x but all squared. Okay, and so you can use your algebra skill to verify me with that. But like I said, even though right now I wrote like this, I want you to keep in the back of your mind that this term came out from that as a square. This term came out from that as a square again. I pointed that out for a reason. Okay, and so now back to what I was in the middle of saying. Then canceling out the 1 with 1/2 for here, our square root in the next step becomes, so here is an integral from minus natural log of 3 to natural log of 3. Okay, and now here we're looking at only 1/4 e to the 10x. Okay, 1/4 times e to the 10x plus 1/2 plus 1/4 times e to the minus 10x. Okay, dx. All right, and so now I mentioned about this term is, think of that term as a 1/2 times e to the 5x squared for a reason. Okay, and I also mentioned that this term, keep in the back of your mind that this term is the same as, can be thought of as a 1/2 times e to the negative 5x all squared. I mentioned that for a reason, because now once we see this, the first term as a square, the last term as a square, allow me to erase, allow me to write that in a little bit of a more spaced out setting right here. Okay, but quickly on scratch work. This first term is the same as a 1/2 e to the 5x all squared. Okay, this last term, that's what the first term is for. This last term is the same as 1/2 e to the negative 5x all squared. Okay, so this 1/2 right here, surprisingly, it's only a constant term, but this is algebraically what we can do with that. So it's everywhere in any step, anywhere you're moving in calculus, especially if we're learning with, if anyone is learning with me right here, anywhere you're going, you will keep seeing more algebraic experience that I'm trying to pass it down to my students right there. Okay, so this 1/2 right here, algebraically, you can see this as a 2 times a 1/2 e to the 5x times 1/2 e to the negative 5x. So basically, surprisingly, that 1/2 as a constant term, but I'm seeing that. I thought of that as the product of these two terms without the square. I'm talking about the product of these two terms without the square. So that first term here without the square is just this 1/2 e to the 5x. The last term without the square is just 1/2 e to the negative 5x without the square. So the 1/2 here in the middle, I'm seeing that, I'm thinking of that, I'm viewing that as 2 times the first term without the square multiplied with the last term without the square, and that's the product right there. Because I mean, algebraically, if we multiply through, it's all going to cancel out and become a 1/2. But I purposely re-expressed that 1/2 as something like that. I purposely rewrote this 1/2 as 2 times 1/2 e to the 5x times another 1/2 e to the negative 5x. Okay, but so why am I doing such a crazy? You don't see this very commonly in your daily algebra, but now anyone viewing this video, you're on your way to keep becoming more mature and mature in math. So start learning, start picking up algebra tricks here and there. Okay, so this is algebra stuff, but it's the kind of trick that not commonly seen. So I'm trying to hand it down to my students who are learning with me. But so why am I doing this? as a matter of fact, if we have a closer look, this is a perfect square right here. It's a perfect square in the form of a squared plus 2ab plus, I forgot a plus sign right there, plus b squared right there. And that's, so all this trinomial right here really reduces down to, so in other words, now allow me to erase this because I'm running short of board space. But the three terms there, after seeing my explanation that I just now had to erase away, the three terms in there form into, so inside the square root, the three terms there form into a 1/2 e to the 5x plus 1/2 e to the minus 5x all square. That's what I wanted to see. So now think ahead. The square root here will eventually cancel with that square right there. But then in the end, we're still working on an integral, an undone and unfinished integral. So from minus natural log of 3 to positive natural log of 3. Okay, so now at this point, we can algebraically move on one more step in the sense that we're gonna cancel the square root with that square right there. Okay, and so in my next step, I'm gonna produce it's an integral from natural log of 3, I mean not minus natural log of 3 to natural log of 3, but the integral now is surprisingly simple. 1/2 e to the 5x plus 1/2 e to the minus 5x dx. And so now anyone with just some basic understanding of your calculus 1, would anyone who's only retaining some basic understanding of calculus 1 can still find the antiderivative of this. Okay, because what is the antiderivative of e to the 5x? It's just going to be the 1/5, as we've learned, I did this back in the days that we were doing the general antiderivative rules as well. Okay, so the coefficient stays here. E to the 5x as the antiderivative, it's going to give us e to the 5x with a multiplied with a 1/5 power. So all of that explanation, let's get to it. And so now I'm going to move on to this board right here. All right. And so now we have, according to the fundamental theorem of calculus, first term gives me a 1/10 e to the 5x. Okay. The next term gives me minus 1/10 times e to the minus 5x. That's the antiderivative of that function here. Okay, and so now I am going to, according to the fundamental theorem of calculus, we are going to evaluate this antiderivative at from minus natural log of 3 to positive natural log of 3. Okay, and so that means now we are quite ready for that. So in the next step, and for a problem like this, I don't even think I need to step out for a calculation on my computer station, at my computer station. Let's look at how nice it turns out right here. So now I'm going to, according to the fundamental theorem of calculus, I am going to substitute natural log of 3 into the antiderivative first. So now what I'm looking at is a 1/10, okay, times e to the 5 times natural log of 3, okay, minus 1/10, and I should have kept that in parentheses, times e to the minus 5 times natural log of 3. Okay, that's the antiderivative evaluated at the upper limit of our integral. And then I'm going to subtract. Now we're looking at 1/10 times e to the 5 times minus natural log of 3. All right, and then the minus 1/10 times e to the minus 5 times minus natural log of 3. All right, and so we have a lot of things going on here, but now let me break it down. That's why the algebra is such an important tool that anyone would definitely need in order to move on with any calculus course smoothly. Okay, so you definitely gotta get your algebra skills going. Okay, and so now first term, e to the 5 times 5 times natural log of 3 in that parentheses right there, it's all the same as So that's going to be 1/10 times 3 to the 5th power. That's what it is. Okay, and then this next term, minus 1/10 times 3 to the negative 5 power. Okay, and then I'm going to subtract, and then allow me to remove the brackets with changing signs and switching signs as well. So here I'm looking at 1/10. That first term becomes 1/10 times times minus 3 to the 5th power. Okay, and then I have to correct this, but it's supposedly 3 to the negative 5 power. Okay, and then the next one here is going to be again. Now in the in the power here is minus with the minus, so it's positive. So it's really just 1/10 minus 1/10 times 3 to the positive 5 power. Okay. All right, and so now, and this is here a plus. Okay, due to that subtraction sign right there. All right, and so now we are going to get ready for the final calculation right there. And so with a little bit of space right there that I need, having a little bit of hard time finding enough space to write this down. Okay, so 3 to the 5th and another 3 to the 5th over 10 right there. Okay, so that's going to make it 243 over 10 minus 1 over, and that's 3 to the negative 5 right there is a 10. Is 1, that is 2,430 in the denominator. And then there's another minus, so that's one right here is another minus 1 over 2,430. Okay, and then we're going to add with 243 over 10. So these two added together, okay, and then these two combined like terms all together. So that's the basic calculation right there. So with the final answer, looking at 486 over 10 minus 2 over 2,430. All right, so final calculation came out to be 59048 over 1215. Okay, because I decided to write this in fractions, so making common denominator and all that and subtract it out. That's our final answer in reduced fractions. All right, and so that's how we're doing this problem right there. The challenging part of this problem is to, first of all, about the wording, then the way how it's worded right here, it's intended that, we're not only setting up the integral, but there is also a way to get through and evaluate that the complete integral setup right there. And so the main challenge about this integral is that we have to use the algebra. So this part right here is our f prime. Okay, and so f prime squared, and so that's our complete integral setup. So the work for that is we have to use the algebra. Okay, so this is a little bit of a special problem. It's special on its own right here, and so observe this way so that just somewhere here and there when you're facing a problem like that, then it will give you a way of handling that with the algebra like that. Okay, so the main challenge of that is the algebra. But once we have the algebra done, then it's surprisingly simplified down to something very simple to calculate the antiderivative. And so now when it comes over to this step right here, then antiderivative is just that simple, and we can get that easily with basic count 1 material, count 1 understanding together with the very basic understanding of antiderivative, and we can get to that. Okay, and then according to the fundamental theorem of calculus, and you can see that I was also doing the actual calculation on the board right here, so that you can see that these problems can turn out nice, once we're patient enough with the algebra. Okay. And so now let's look at example 2. All right, and so now let's look at example 3 right here. So now we want, so it's the same setting, pretty much the same similar wording description right here. In example 3, I want to find the arc length of, and the curve we are given here is y equals natural log of 1/2 natural log of, there's a 2x minus square root of 4x squared minus 1. Okay, and then so we want to find the arc length, basically the part of the graph, the piece of the graph on this function here, but only inside the interval from 1/2 to 6 right here. Okay, only from 1/2 to 6. And then in this problem right here, so it's very similar to example 2 that we have done previously, but in this problem allow me to add on a little bit of extra information, an extra indication. So be aware of that you might run into the exercising problems, or you might run into actual problems out there where you are indicated, where you are instructed to do the following. So by integrating, okay, so we want to find the arc length by integrating in respect to y. Okay, so by integrating in respect to y. All right, so now again, it's an arc length problem, a problem where we need to find the length of the arc. And then back to the beginning again, we have two choices. We can, if our curve is already expressed, if we want to integrate, if we want to find the arc length, if we want to set up the integral to integrate in respect to x, then we use this formula. Square root of 1 plus f prime of x square dx inside the square root, and then from a to b. That's one choice. But this is if we are intending, if we're planning to integrate in respect to x. Okay, and then as another choice, we have the following formula. Length of that same curve right here can be found by integrating over the interval from c to d on the y-axis with the following function: square root of 1 plus, and now g prime of y all square. Okay, and dy. So this is here integrating in respect to y. So we have two different choices. So this problem, if this problem was given without this indication that I'm putting my arm over to cover it, if this problem was given without this indication, then we have two choices, and you can make your choice. But now with this problem, it's already routed down for us. It's indicated clearly that we want to set up the integral so that we can calculate or we can integrate in respect to y. That means we cannot use this choice of the formula. So this choice of the formula now must be erased out. So the real choice is here. Okay, so that's the work, and that's the experience that I want my students to learn from this style of wording. And then so just like how it was in example 2, the problem here does also intend that you can go, once you have your integral successfully set up, you can go all the way to the end and find your final numerical answer for this. Okay, and so now the real challenge here is that this problem in the beginning, this curve in the beginning is expressed as a function of x. But sadly that choice is out. We're not allowed to go with that choice integrating in respect to x. So we have to integrate in respect to y here. That's according to the request, to the requirements of the problem. Okay, and so now we're going to have to use the algebra again to re-express this function, this curve in terms of x. In terms of y. Right now it's in terms of x, and we have to re-express that curve in terms of y so that it's suitable for using in this formula, because we need to find out how we can re-express this curve as a function g of y so that we can take the g prime of y and all that. Okay, So I'm going to now navigate to my other board and to show everyone the algebra that turned this equation, okay, that turns this equation into an expression in terms of y, a function in terms of y, so that making it ready for this. And we also be aware that we also need to convert this interval, because right now this interval is in terms of x, is on the x-axis. We also need to find a way to convert this interval in terms of y, okay, and so that will come later as well. All right, so on my other board, let's look at the algebra. So the part here is completely about the algebra, okay? And so for calculus students who are viewing this lesson, if you feel strong with your algebra, then you can indeed fast forward this part of the video lesson right here to skip and to challenge your own on the algebra, okay? Because our main goal is to see with our equation currently written as y equal 1/2 times natural log of 2x minus square root of 4x squared minus 1. Okay, so before, how about you, if you feel strong with your own algebra, you can fast forward this step right here. Okay, but otherwise you can follow along with with that part right here. But we want to re-express this as x equals an expression, okay, of y. That's what we want to ultimately end up with. Right now we have y equals an expression involving x. And that's the idea right there. Okay, so it takes quite a few steps, and we want to find out what that expression in terms of y is. Okay, so now let's have a look at, so observation is telling me that this 1/2 right here, we can multiply both sides by 2 to clear out that 1/2 fraction. So we're looking at 2y equals natural log of 2x minus square root of 4x squared minus 1. That's already made, that's simply that little work right there already made it a lot simpler, the equation a lot simpler, because we cleared out the fraction. Okay, and then but now all of our x terms are inside of the logarithm, so I want to get rid of that logarithm. Okay, so the way of doing that, I'm going to raise both sides of this equation to be the exponential part of the e function. So now on the left hand side, I'm producing e to the 2y equal, now it's just simply 2x minus natural log of 4x squared minus 1. And I believe you shouldn't be new to this. Okay, anytime you have an expression that involves logarithm, this is the equivalent form, but in exponential form. Okay, your algebra course should have covered all that. But here we're going to see how we effectively use that for a much more advanced class as what we're in right now. Okay, and so in this way right here, the next step I'm seeing, I am going to, see, there's a square root right here. There's a square root, so the only way to get rid of square root is to take the square of both sides. Take the square of both sides. But let's not rush. Taking the square of both sides right from this step right here is a little too rush. Okay, that's not a good plan. So this is how this is what I'm doing right here. I'm going to rearrange this same equation. I'm going to rearrange so that square root stands by itself. Okay, because otherwise right now there are two terms. One term is with the square root, the other term is non-square root. So squaring both sides is gonna make it more complicated. So I want you to just simply rearrange this current equation to the form where square root stands as one term on its own on one side, and then everything else on the opposite side. That's what I'm doing. And so now right now I see a negative square root, so I don't want to keep that negative square root here. I bring that square root term to the other side, making it positive 4x squared minus 1. Okay, and then this term right here, and like I said, once I have isolated the square root to one side, I want to bring anybody else to the opposite side. So on the opposite side, I have that 2x, and then I have that, I'm going to subtract over that e to the 2y. Yes, admittedly, our equation here is x and y all over, crazy. Okay, but it will get us there. So be patient on the algebra here. But now the point again, I have just explained. Here we got the square root on one side, one single term with the square root. That's good work, because this equation previously, this step previously had only one the square root term. So we desire to keep that square root term, that lone square root term on one side be positive, and then everybody else is on the opposite side. Okay, And so from that way right here, I'm going to square. Now it's good that we square both sides effectively right here. So squaring the left-hand side, see, so now I'm going to square both sides. All right, so squaring the left-hand side, now it gives me 4x squared minus 1. It's just the square root is canceled out. That's what the usefulness of the squaring both sides is. And now the right-hand side, we're going to need to spend some time doing the foiling out of this perfect square right there. So first term after the square, and your algebra should be, at this point, should be strong enough to go through this on your own right here. So I'm going to allow me to go brief on that, okay? And you can double check with me. So this first term after the square gives me 4x squared, okay? And then the squaring, anytime we're squaring out a binomial, we will always end up with. So in this case, I'm going to look at the middle term being a minus 4x times e to the 2y. Okay, and then I'm going to produce that there will be a last term for me, which is a plus right here. And like I said, you don't have to believe me blindly. You can always proceed on your own and double check with my algebra over here. Okay, and it's all the algebra that came out. So e to the 4x is what I see here. I mean e to the 4y. It's the last term after foiling out this. So just a little advice. Think of the square here as 2x minus e to the 2y times itself 2x minus e to the 2y. That's what I keep saying. That's what I meant by keep saying foiling out. We see this square as two identical factors and FOIL out. So after foiling out, we should get something like this. You can double check my algebra on that. Okay, so now I'm going to clear this away because we need space. But now at this point right here, I have identical term on both sides. I'm going to cancel that away. Okay, and then remember, we want to solve for x. We want to solve for x in terms of y. So that term here is already only in terms of y. So let's leave it there. That term is gone. That term is gone. This term is a constant term independent with x, y. We can bring that to the same side with this lone term. But then this is the only term that has the x, variable. So I'm going to bring that term to the opposite side. So in other words, in my next step, here's what I produce. So I'm going to bring that, so that 4x squared is gone. I'm going to bring this term to the left side and add that 1 to the other side. So now I'm looking at 4x times e to the 2y on the left equal 1 plus, and that minus 1, after being brought to the other side, it's going to become a positive sign. Okay, and your algebra is what explains for that. And then plus e to the 4y. Okay, and so now we're getting closer. So now all I'm doing to solve for x, I'm going to divide both sides here by 4 times e to the 2y. Okay, so dividing both sides by 4 e to the 2y, I'm looking at, or maybe let me just spend some extra step to make it real clear right here. So from our current point, 4x e to the 2y, that equals 1 plus e to the 4y. I am going to divide both sides by 4 e to the 2y. That's how I solve for x. All right, so left-hand side now simply gives me just x. We're getting there. Okay, one single lonely x variable equals, now left-hand side is a 1 over 4 e to the 2y plus, and then that here is a 1 over 4, 1 over 4 times e to the, see, if we're canceling 4 e to the 4y with e to the 2y here, it's going to become e to the positive 2y. That's left behind like that. And then the 1 over 4 e to the 2y is indeed, this is the same as 1/4 times e to the minus 2y. And then the next term here is 1/4 times e to the 2y. All right, so this is our function x in terms of y. And so in that way, now back to my other board. So we have almost everything we need right here. So the formula now needs g prime of y. This is our g prime of y right here. This is now our g prime of y. We can see that. This is our g of y. This is now our g of y being a 1/4 e to the minus 2y plus another 1/4 e to the 2y. And so now we're just simply going to take the derivative of that. Okay, so now our basic derivative understanding, we can get, so g prime is going to give me, a negative 1/2 e to the minus 2y plus 1/2 times e to the positive 2y. Or I can rewrite this. I can rewrite this as a positive. It's just me. I prefer to write positive term first to be the start. So 1/2 e to the 2y minus 1/2 e to the minus 2y. That's my g prime right there. Okay, and so now allow me to quickly erase this, and then we're gonna, or we don't have to. So now the integral is going to be the following: from some c to d, square root of 1 plus, and now 1/2 e to the 2y minus 1/2 e to the negative 2y all squared, because that's g prime squared according to the formula. All right, so we almost complete with our setup of the integral over here. Okay, and so now we need to convert this interval, because currently it's in terms of y, it's in terms of x on the x-axis. We need to convert that into the equivalent interval on the y-axis. Okay, so it's actually simpler than anybody viewing this video thought right here. Let me swing to the other board and get that work quickly done right here. All right, so our function our curve started out giving us y equal 1/2 natural log of 2x minus square root of 4x squared minus 1. So if when x equals 1/2, this is the beginning of our interval over here. When x equals 1/2, what's the y value can be? What can the y value be? Okay, we're going to substitute that into our expression here. So that means we're looking at, so y equals, so the calculation here goes 1/2 times natural log of, this is 2 times 1/2 minus, and in parentheses, in square root, we have 4 times 1/2 all square minus 1. Okay, 1/2 all square minus 1. So, and 1/2 square is a 1/4 times 4, it's a 1 minus 1. So the square root expression in the next step, so this cancels to become a 1. Okay, minus square root of 1 minus 1, because 4 cancel with that. 1/2 squared is 1, so the square root here will eventually become a 0. So it's a 1/2 times natural log of 1, or it's all a 0 out. So this is a y value. That's one y value. Okay, let's look at the other value. And now I'm going to quickly erase this. All right, so for the other value, when x equals 6, let's find out what's going to happen. Y equals 1/2 natural log 2 times 6, okay, minus square root 4 times 6 squared minus 1. All right, and so here it's giving me 1/2 natural log of there's a 12 here minus a square root, and that is making it 144 minus 1, which is altogether square root. 143 square root of 143. So here it's 1/2 times natural log of 12 minus square root of 143. Okay, that's fair enough with that expression right there. Okay, and so now that's our upper limits, and so later on, so that means now in this integral, we're looking at an integral from 0 on the y-axis, okay, to here is 1/2 natural log of 12 minus square root of 143. All right. Okay, so, and that's how the complete setup is. Okay. All right, and so now I'm going to take the next board space to evaluate the integral. So according to the problem, this integral once set up, we can evaluate all the way to the end. So here's our integral. It's from 0 to 1/2 natural log of 12 minus square root of 143. Okay, and the integral here is a square root of 1 plus, and then that 1/2 e to the 2y minus that 1/2 e to the minus 2y all square dy. So let me now mention, and so there's a reason why, before I made the video lesson here, there's a reason why I structure these examples with the, example 1, 2, and 3. They're all connected. Okay, I put this problem here as example 3 after example 2 because I want you to see that there's some experience from example 2 that we can carry over. Okay, especially if we have a closer look in here, and if you can go ahead and roll back to the example 2, then that part of example 2 is very similar to the work we do in here. So with that same experience we have handled, with that same experience how we handle this expression inside the square root, we can apply that here. Okay, so at any point, if you need to roll back on this video and roll back to that earlier example 2 to see how I can algebraically work on this problem right here, then feel free to do that. Okay, because here I'm going to go a little skippy. So from that experience, so now I'm saying from that experience we have done with the algebra, it's all the algebra to handle this. Okay, so from that experience that we use the algebra from example 2 right here, then we can do the similar thing. So this overall square, after foiling out and add it with that 1, I can rewrite all that integral as, this is now square root. All of that expression inside the square root can be reduced to a perfect square being a 1/2 e to the 2y, but now no more minus, it's now a plus actually. So 1/2 e to the minus 2y all square dy. Okay, so if you can roll back to that example 2, see how I did something similar to this, and you will understand. And this is 1/2 natural log of 12 minus square root of 143. Okay, so now square root will cancel with that square, which will give me an integral from 0 to 1/2 natural log of 12 minus square root of 143. Okay, and then here we're looking at now just simply a 1/2 e to the 2y plus 1/2 e to the minus 2y with a dy. All right, so the integral here is easy to find the antiderivative. And so now, according to the fundamental theorem of calculus, antiderivative for the first function here is going to be a 1/4 e to the 2y plus, and indeed it's a minus 1/4 e to the minus 2y. Okay, and then we're going to evaluate this antiderivative from the two limits right here, from 0 to the 1/2 natural log of 12 minus square root of 143, which is a little lengthy. That I'm running out of space here. 1/2 natural log of 12 minus square root 143. Okay, and so because of the lengthy expression here, so this problem right here, it makes perfect sense that we can, when we came to this point right here, then we can use a technology of some kind to help us do the calculation, especially when it's a value here, but it's just value expressed as an expression instead of a lay down a numerical value like that. So feel free to use your technology. I will swing by my computer station to grab a final answer for this. But basically we're going to substitute that value into the function for y, into the antiderivative for y, and we're going to do that again for 0, substitute it into the antiderivative and subtract out the 2. It's a minus here actually. Okay. All right, and so now let's get ready to grab the final answer. All right, and so as a matter of fact, when I was there at the computer station, I found an error of mine right here, that I should have also done that prior to this point and letting the error drag a little too far. But it's also a good experience so that you can learn that even instructor make mistakes, and something that motivates anyone learning from the video here to really be responsible on your own to double check with this. But here's the experience. I actually have misplaced these two integral values. I mean, the way we found them was completely correct, but I misplaced them due to one error of mine. I forgot to check the value between these, that who's larger than the other one. So it's a very understandable error that a lot of times, since we see large expression, we tend to think it's a big value. Okay, it's the way it is. But so being a large expression here, but if we punch this value into the calculator a little carefully, it's actually a negative value. This is a negative value. This is a negative value. That's a negative value. So the integral should have been, and I should have done that when right at the moment I found these. I should have double checked that, quickly punch these into the calculator and found out who's bigger and who's smaller, because we always want larger value on top and smaller value at the bottom. Okay, and so this time, according to the calculation, this expression is indeed a negative, and I should have checked that right at the moment I found these values on the y-axis. And so the integral initially should have been, the integral originally should have been one half at the bottom times natural log of that 12 minus square root 143. Okay, and the upper limits is the 0 value right there. Okay, because that should have been the other way. All right, and so now just like that, there's the 1/2 natural log of 12 minus square root 143 is the bottom end of our integral. All right, and so and that's what it is. 1/2 natural log of 12 minus square root 143, and then 0. And so consequently, it means the same thing here for this step right there. I'm going to put 0 at the top, and here it's a 1/2 natural log of 12 minus square root 143. All right, and then after looking at the calculation result from the computer station there, then I came to 5.979 in 3 decimal places. All right, and that should be the final answer. And so that's the length of our arc right there. Okay, and so again, I need to remind, I went really skippy from with the steps between these two, because we've had that experience back in example 2. And so if you're still feeling unsure, if you want to find out, if you want to unlock how I gone from here to here, go ahead and review the experience we did in example 2. And so I brought up this example as an example after example 2 for a reason, that it has that similarity, some experience that we can carry over from example 2 into this particular problem. Okay.